Hi, I've got a few issues to solve. These next few videos are going to be related to getting that taken care of so we can move forward with a clean system. In video 36, I started talking about needing a new clock module, and here we are at video 64, and well, that time is now. In video 58, I talked about needing a replacement to the custom EEPROM that I was building, and I also talked about my GPRs not having an end latch for the reset, so I needed to take that into account as I was writing code. I want to address that today as well. In video 59, I alluded to some issues with the power supervisor, and while those have seemingly gone away by adding a few extra connections for power and ground, there's something that's brewing there I need to look into, and I don't want to let it go much farther than that. And I've got some pretty egregious control logic timing concerns related to the end latch signal, where I've got a massive delay built into that. I need to get to the root of that as well and make sure that I'm doing the right thing there. In the last video, I talked about the reset logic needing to be redone, and then I was not comfortable with some of the instruction timing and steps and making sure that all of that is happening the way that I need it to. So in this video, or at least this video, starts a 2-video series, maybe 3, depending on how long it takes to get things stabilized. And I want to look at the clock module. I want to look at the GPRs and latch signal for the no-op. And I want to look at the reset logic redo. I believe that's going to take 2 videos to get through, but maybe I'll be efficient for once and get it done faster. Efficiency in these, I've always overestimated my ability to get things done and get them done cleanly the first time, and so I'm trying to be a little bit more conservative with this, saying that I need at least 2 to get through these. Got a lot to do, so let's get right into it.
Hi, my name is Adam. I'm building a 16-bit computer from scratch. I hope you'll join me on this journey.
Okay, so the clock circuit. James Sharman used a version of Julian Illett's clock, and Julian published the schematic to his clock. I'll include a link in the description and one up in the cards there. And this is what I want to start with. This is the starting point I want to go with my clock. So I want to make sure that you go and watch Julian's video on pulling this together and testing it. I'm still going to use a 556 IC because I believe I'm going to need to have 2 timers running on this. Of course, I need to decouple that. Julian has a 1K ohm resistor here to connect VCC to the sweep. And then I've got a 1 meg ohm variable resistor here. It's same one that I used in my previous clock circuit. Now he's got a 200K. I'm going to use a 1 meg ohm to give me just a little bit wider range of frequencies here. And then for a capacitor, I'm going to use a 0.1 microfarad, where he's got a 1 microfarad. So I'll get some faster clock times here. Now I've got a fresh breadboard here, and I've already hooked up power. I've got the decoupling caps in here. And so I'm just going to go ahead and drop this 556 in here with its decoupling. And this is a little bit different than the 555. Power and ground are actually right where you would expect them to be for any of the 74 series logic. So I'm going to go ahead and hook those up. And then I'm going to drop in my variable resistor here. This is going to be my control point. Now from ground up to pin 2 is the capacitor. And then from pin 2 to pin, well, it's supposed to be 6, but nope. I should restate that because I'm looking at his pin, but it's not really what I want. So he has the capacitor from ground to the trigger and threshold tied together. Pin 2 for me is threshold, and trigger is pin 6. So I can tie those together. Those will work just fine, or I can move my capacitor over there. The other side of threshold, pin 6, is going to go from here to one end of the variable resistor. The other end of the variable resistor is going to come up to 5 volts. And then the sweep is going to be tied to 5 volts using, let's do it, back it up this way. The sweep is going to be connected using this 1K ohm resistor, and that'll be connected to 5 volts. Now that's right underneath where I've got this. Now my output is on pin 5 here, so this should be the output. If I pull that over here, I should be able to put in an LED. I'm thinking here because I'm trying to figure out exactly how I want to put this resistor in here, because I need to current limit that as well. My reset, which is pin 3, probably needs to be tied high. Okay, now having gotten this put together, I want to go through quickly here what I'm observing. And this is still Julian's clock. Here is my fastest speed. I end up with 11.6 kilohertz, which is a good speed if I'm going to run anything in test. But take a look at the clock, the shape of that clock cycle. That square wave is not symmetric at all. I've got a very long duty cycle high and a very short duty cycle low. If anything, I actually need that duty cycle reversed. I could run it through an inverter, but that doesn't make a lot of sense. Now, as I turn this clock speed down so it gets slower, and eventually I get so slow that it just bottoms out and stops. But again, take a look at this clock cycle. This is more in line with what I need, but it's at slower speeds, so it really doesn't matter. And the duty cycle is far shorter high than it is low. And I'm trying to get to something that's far closer to a 50% duty cycle. So half the time is spent high and half the time is spent low, no matter how fast I go. At this point, I'm going to tear this out, and I have a Texas Instruments wire up. This is also a 50%, this is supposed to be a 50% duty cycle. For this timer, I am going to use an LED to see what's going on for now. So this will be tied to the output, one of these two outputs. I'll have to measure which one gives me the better signaling. I am still planning on using a 556 IC because I've got a need for 2 timers, and I'll get into that a little bit later as we get into this. And of course, I need to decouple that. My resistor here is a 1000K ohm resistor, but this capacitor down here is a 0.01 microfarad capacitor is what I plan on using. So this is going to charge quickly and discharge quickly. And instead of this resistor here, I'm planning on using 2 leads of this potentiometer. So I've basically got a variable resistor. I'm not going to connect the 2 ends together. I'm going to connect only 2 of the middle pin with one end or the other. So it's a variable resistor. Let me get this wired up, and we'll see if I can actually make this thing oscillate a little bit. Okay, I'm back in chronological sequence again. So once again, this will flash and it oscillates properly. I want to take a look at the shape of the square wave here. This is my ground connection, my output. Shape of this square wave isn't fantastic. It's got the same problem, it looks like, as the other one did. But if I speed this up, there we go. That still at least has the same shape. In other words, the high side of the cycle is longer than the low side of the cycle. And once again, what I'm looking at here is the sequence of how the signals need to take place. And I'm thinking about the program counter in particular. The increment and latch happens on the falling edge, which means that at that point it's got to update the EEPROM or the memory in order to get the new data out, and then that data, which would be the instruction into the fetch register, would be latched on the rising edge. I really think this would actually be a beneficial square wave and distribution of duty, if you will, if this were inverted. So let me throw an inverter in here and I'll demonstrate what it is that I'm talking about here. And then measure the output of the inverter. It's jumping around a little bit, but that's a little bit better because now on the falling edge, I can increment and latch, and I've got a much wider space to resolve that new address before I latch it at the fetch register. So I think that's going to end up working out better for me. My other concern is the ALU. Well, now I've just contradicted myself. So the challenge here becomes the ALU has just that short of a period of time to handle the work that it needs to do before it gets latched. All right, not a fan of that. Let me see what I can do, because this 50% duty cycle isn't, well, what happens if I tie reset high? Is that in run? That didn't help. And if I put the 0.01 microfarad capacitor here on control, that doesn't do much either. 50%, you're almost 3.5 to 1.5. That's quite off. All right, let me go build out a traditional astable circuit. I'll find a diagram of that too. Okay, here's to hoping third time is the charm. So this is a traditional astable timer circuit. The load is over here tied either between the output pin and 5 volts or the output pin and ground. So we can ignore that portion of it for now. Pulling up my pin diagram so I can look at it while I'm wiring it up. And of course, I'll stick that up in the corner for you. It says here the external capacitor charges through RA plus RB and discharges through RB. RB being the variable resistor that I'm going to use to control time. So that needs to be tied between the discharge and the threshold pin. So this is going to go between pin 1 and pin 2. So discharge being pin 1, threshold being pin 2. And I believe the proper way to hook that up is there, but I can always change that as well. I'm just going to borrow a 220 ohm resistor for now. Either of those will work. I'm going to hook this up 5 volts to discharge. I am curious, and I will test this. If RA is 0, then I should have a 50% duty cycle as well. And the capacitor goes then from threshold to ground. Now again, threshold and trigger being pin 6, are hooked together. I've got VCC, and reset is explicitly tied to 5 volts in this circuit. And I'm going to go ahead and connect the control pin to ground on the 0.01 microfarad capacitor as well. So that then gives me my output, which is here on pin 5 again. Bring that over and insert the LED, and then I should have an oscillating circuit, unless I have that in backwards. There we go. So that oscillates much better. I don't have a signal that deteriorates as I get faster, and that looks good. So the question I have then is, what happens if I tie this to 5 volts directly? It does not oscillate, so I do need a small resistor in there. I'll try keeping the 220 ohm. Let's see what that does as I look at it on the scope. And that's not 50% at all. Well, but I've got this 220 ohm resistor, which makes it asymmetrical. If I speed it up, I am still... What happens if I put a 1000 ohm resistor in there? Yeah, that makes it even bigger. So what happens if I go get myself a... This is the smallest resistor I have, and this is a 10 ohm resistor. And that won't allow it to oscillate. Okay, this is a 100 ohm resistor. And again, that won't allow it to oscillate. 220 does allow it to oscillate. Alright, so I've got 3 divisions here. 1, 2, 3, 4, 5, 6 divisions there. So it's literally 1/3, 2/3. So what kind of range do I have? 21 kilohertz, and that's my high end. And that's 3 hertz at the lowest end. I like that range, I just don't like the shape of the square wave. Alright, I have one more trick to try. Okay, this is the data sheet for a 74LS74, and what I want to call attention to is the function table here. And specifically the clock on the rising edge is going to latch the data and output the data onto pin Q, which is going to be pin 13. But if I'm reading this correctly, if I take the inverse of Q and feed it back into the data to be latched, I should end up having something that's going to toggle back and forth between on and off on every rising edge, such that it stabilizes the clock such that I have a true 50% duty cycle. Let's put this on the breadboard. Okay, so here is a 74LS74, and it's brand new, so I gotta roll the pins. Okay, power and ground, and I will decouple that, or add decoupling here shortly. If I take clear and tie that high, because it is an active low signal, and preset, which is on pin 4, and tie that also high, because it is also an active low signal. And if I take my output here from pin 5 and tie that to the clock, which is on pin 3, which then I can take my LED out. What else is it? It is the inverted Q, which is going to be pin 6, goes to data, which is pin 2. Then my Q output here, which is pin 5. If I bring that out and put the LED in there, I still get a good oscillator. But now I should be able to measure that and see a 50% duty cycle. So let's give that a shot. So I'm going to plug this in here. That looks very much like 50%. Let's speed that up just a hair. Yeah, that definitely looks like 50%. Now, I'll be honest, this isn't the way I expected this to go when I sat down to put this together. I was genuinely hoping to be able to stick a double pole, double throw switch in here. I'm sorry, single pole, double throw switch in here, and be able to single step that way. With this on here, the D-type latch, I'm going to have to click this once in order to get moved to a low cycle to a high cycle, and click it again in order to move from high to low. And so it's basically going to be a half step every time I press the switch button there. That said, I actually think I'm good with that, because how many times have you seen me hold the clock button down while I'm trying to probe around with my other hand and do stuff and check things out, and then only to accidentally release it or release it? So I think I'll be okay with that. The only thing I might have to train myself to do is make sure that I check to see if I'm at the high cycle or the low cycle when I stop it, or come up with some way to force it to stop when it's low only. Let me do some cleanup here and get this wired up and set so that I can actually move on to the next thing, which would be single step. Okay, Julian's circuit has this switch here, which then puts us into a single step switch, which would be this single pole double throw. And so I'm going to tie this in right now, or for the moment here, and effectively what I'm going to do is I'm going to take the threshold and tie it into the common pin, and then with a couple of 1K ohm resistors, tie one side high, and the other side I'm going to tie low. And then so every time I push the button, it changes state from high to low or from low to high. And ultimately what it boils down to is this clock is clocking once every time I push this, but it takes 2 clock cycles for the D-type latch to latch itself. Now, I want to try to improve that a little bit, in such that it will run up until the point in time that I end up in a low state, and then it'll switch from run mode to not run mode. In order to do that, I think I want to build out this other timer circuit here so that it's constantly running, and I will also end up using this as part of the reset circuitry. So let me get this one built out. Okay, that's oscillating just fine at a frequency of 80 times per second. Now these are 1K ohm resistors, and I can drop those down to, say, 220 ohms, and I think get a better response. So let's try that. So that's 81 kilohertz instead of 81 hertz. So that's actually really a nice speed. I like that speed. Now I could probably put 100 ohm resistors in there and get maybe twice the speed, but I think that'll work just fine. Okay, next up I want to have a little bit of state here, and I want to be able to select run mode versus half step mode, if you will. And so I want to create a couple of buttons, a little decoupling there. I want to pull those high with a couple of 1K ohm resistors. And then here I want to create, let me get power and ground. I want to create a set reset latch. And these are literally just one bit of state where the output of one NAND gate goes into the input of another. And then I have one input reset, and this one is the set. Now I don't need this anymore, which I can now pull over here. This should be my Q output. Okay, something's not quite right here. I gotta pull those low. There it is. So set and reset. So single step or step mode and run mode. That's how I'm going to remember that. Okay, the next thing I want to do is I want to duplicate this clock divider up here on the upper half for the high speed. And basically it's going to be an exact copy of what's going on down here. So again, clear, tied high. Preset tied high. That's not high, Adam. The data and the Q, inverted Q, get tied together. I need a longer line for that. This then is the output, which then I can tie to an LED to see what's going on. How much do you want to bet you put that LED in backwards? And then the clock itself is going to come from there. I've already got one there. All right, so you can plug it in. Flip the LED around because I think I had it in backwards. And then we can measure here. And so now I'm measuring the output here. And I'm nothing but high. So let's see here, clock. Where was my output on that? output is on the rightmost. So my reset should be tied high, and my output comes over here to the clock. And the clock is... Oops, I've got one of them. There we go. Something's not right. I'm seeing some real odd stuff here, and I'm wondering if that's better. Much better. All right. So with that done, then I'm going to perform a quick cleanup of this circuit, get everything wired in more permanently, and then we'll address the single step. That's coming out for now. I will put that back in after this. Let me get this cleaned up. Okay, while I'm working on this cleanup, I got to admit I was not expecting this circuit to end up this complicated. I certainly didn't expect it to take nearly the entire video to get a working timer circuit. I guess it goes to show I was under engineering for once in my life. Okay, next up is the single step switch. And I'm going to drop this in, say right here. I need to make sure that I've got access to it from the right hand side, the outside of the board. So that's probably a better spot for it, at least for now. And then I've got to be able to debalance this. So I'm going to use a 555 timer to do this. And I will drop this in here. And this is pinned very differently than a typical logic IC. Ground is on pin 1 and 5 volts is on pin 8. And so this is where the decoupling needs to go. And I think I cut that a little short. But I can stick it right off here to the left. That'll be just fine. All right. Now, 2 and 6, I believe, need to be tied together. I'm kind of making this up at this point because all I really need to do is have 6 connect here to the common pin, and then one of these connections go low and one go high. And so that should do that, hopefully. And then similar here, I believe on pin 2, or pin 6, either of those, I just need to tie a capacitor low. And that's should be all I need in order to get output. Questioning if I've got that right or not. I don't believe I need the resistor, but I might, because the capacitor itself is going to be charging from here. Okay, that looks reasonable. Now the question is it properly debalanced? And so looking at the yellow LED here, that looks like it's properly debalanced. Let's try the falling edge and try that again. Again, that looks good. So I'm not seeing that. Yeah, I'm not seeing any bouncing going on there. Rising edge. Again, no bouncing. So now the question then becomes, do I want to have this be its own individual clock cycle because I've kind of changed my thought process here? Or do I want to put it through a divider like I've got the other two? And I'm kind of thinking I want to have its own clock cycle, even if I have to hold it down in order to do probing. Well, I tell you what, let me get this cleaned up. This should be relatively quick. And then we'll figure out how to merge these clock cycles, these clocks together using the output of the set reset latch here to do that. Give me a second to get this cleaned up. Okay, I actually got so excited that it all worked the first time, I actually forgot a couple of connections. Pin 4 is reset, and that's active low. And so I want to tie that high so there's no question about whether or not I am in reset. So I'll add that wire. And then pin 5 is the control voltage, and it's recommended to tie that low through a 0.01 microfarad capacitor. And so that goes to pin 5. The final change to make here is I want it such that when I push the button, the clock goes high. And then when I release it, the clock goes low. So that's a simple change here by switching which of the pins goes high and which of the pins goes low through the resistors. And so that's a simple change. All right, the last task here is going to be to select which of these clocks is actually going to make it off to the rest of the circuit. And I'm going to use a 8-line selector slash multiplexer here. There's power and ground. Let me get some decoupling in here. And this is going to be way overkill for what I've got going on here. The first one is the global enable line, or G signal, which is an active low, and I always want this to be enabled, so I'm going to tie that low directly. I think I just cooked this. Let's try this again without actually destroying this IC. The good news is I think I actually had them both tied to ground, so I probably had a neutral circuit. Anyway, global enable, pin 7. It's going to be tied directly low. A, B, and C inputs, which are up here on the top. B and C are going to be tied low, and only pin A is going to be driven from the set reset latch. So that's going to be used to select between outputs A. So with that on, that off, I want A to be the stepped clock. The stepped clock output is from pin 3, and that's going to go to D0. Next one over, D1, will be off the bottom 555 timer here, which is going through this divider. So that's going to be its input. The other 6 options are all tied low, and so I will get those during cleanup. But my output here, which is going to be on Y, and I will pull this up here. Okay, so that should be, I have those backwards. So step and run. So that's a quick fix here. Swap these 2 lines. So step and run. Okay, I'm pretty sure some of this is going to change, but let me get this cleaned up and at least organized for now. All right, I'm going to leave this here for today. I got pretty far into the clock, and I did not get into the reset, and I was hoping to a little bit, but I think I'll be okay with that. The next video will be the reset circuitry and what it takes in order to reset the entire computer down properly. That's going to include some firmware changes. And once that's done, I'm going to feel a lot better about making sure that power on reset and resetting the system actually works properly, and then I can actually get reasonable tests after that. We'll see you soon.